Welcome everyone. Let's continue talking about strain in flexural members, and today we're covering very important aspect of designing beams, something called strain in flexural members, compression control, tension control, transition control. Before that, I have to do a quick introduction about this. We know all from this figure here, we talked about the first session that the strain in concrete, we are assuming in this course that it fails at 0.003. This is the maximum strain of concrete, right? So the strain is concrete is 0.003, but what's the strain of steel? Actually, the strain of steel depends on the grade of steel, which is Fy over the modulus of elasticity of steel, which is fixed 200. So it's 200 gigapascal or 200,000 megapascal over 420 megapascal. It's around 0.002. So it depends on this number. Okay, but usually we use it as 0.002. Now, coming from this, drawing the stress or the strain diagram, we know that the concrete reaches its limit at 0.003, and then the steel depend on which stage is it. Is it yielded? Is it before yielding? So here it is 0.003. That's the concrete, right? The distance from the neutral axis to here, we call it c, small c, which is the distance for concrete compression, and from here to here it's d, which is the beam depth. So this will be d minus c. Okay, so what is the tensile, what is the strain in steel? Is it yielded? Is it, before yielding? Did it work? These are what we mean by compression control, tension control, transition control. It's dependent on which stage in steel we are. Alright, so there's an equation that defines where is this. It's actually ut is 0 d minus c over c multiplied by 0.003. This is an equation. This tells me at which stage the steel is. Alright, so let's define what is tension controlled, compression controlled, and all of these before moving forward in order to understand the calculation and everything. Right, from here, the compression controlled, which is this is the one, first one. I'll number it as 1. Compression control means that the strain in steel is less than or equal than 0.002, less than the yielding. That means this stage is called compression control. As the name indicates, it's for compression members. It's not for beams and slabs. Beams and slabs are tension members. So what does it mean if I use this, if I design my beam based on this? That means the beam can fail suddenly without any warning. I mean by warning, the deflection. When you see a beam or a slab that deflects, this means that it is giving you a warning that I am going under stress, and I am warning you by the deflection. That means there is something wrong. But if there is no deflection and the beam suddenly damaged or fell down, this is really a big problem. It's a sudden failure, so don't use it in your design of tensile members. This is for concrete, for columns, for compression members. Column is a compression member, so it's for columns, not for us, not for beams. Alright, going to the next one. Okay, it's the tension control. Tension control, right here too. Tension control is, this is one. Tension control is the one that we design our beam for. As per the ACI section 10. ACI code 10.3.4, this term, strain in the steel, should be greater than or equal 0.005. in order to be in this zone. This means that the beam will deflect It will give you warnings. It is a ductile. The first one is brittle. It acts as a brittle, although it's a steel, but it's acting as a brittle. Why is that? Imagine that I have a beam. Just go back to the first point number 1. Imagine that I have a beam and I filled it with steel. It is so filled with steel, that means the steel doesn't have even the chance to move or bend. And what does that mean? That means it fails, the beam fails before even the steel felt that there's a problem. So the concrete is crushed and it fell totally, because I filled the beam with the steel. Here in the next one, in this one, which is number 2, I'm putting minimum percentage of steel in order to achieve the ductile and take the tensile loads. This is desirable. We don't want this, we want this. Number 3, transition control. It's simply between 1 and 2. It's not desirable, but it's not too bad. Okay, so we have to consider this we have to understand this. So finally, I want to say, let's assume that we have a line here. Let's draw a line. Okay, in this line we have stations. First station is called is the first one, and the last station is called this one. This is where we have, let's say, this is where we have 0.05, and this is where we have 0.02. So from here going, these are the values of E, the strain. From here it's compression controlled. It's for columns and things like that. It's compression. From here going that, it's tension. It's like it's for beams and slabs. This is the desirable one that we need to do. Between them is the transition zone. It's number 3, which is not desirable also. So what I need you guys to understand, that we are designing a beam that should be ductile, that should be here. If I found in my calculation, my design, E, the strain in steel, is less than 0.05 somewhere here, I need to enhance my design to go back to this area. If I found my strain in steel is somewhere be less than even 0.002, I'm in a really big problem. Okay, that's the end of the session. Thank you for watching. Hope you